That's global stability, correct, not asymptotic
Actually, that's just asymptotic. Oh, you mean if they have no frictional oscillate? Yes. Yeah. Yeah. But if we have a little bit of friction, it's going to push me up. But it still has this, even if I have friction, then I will just be the asymptotically stable runs stable. Okay? Because this thing will return to this origin if I'm up here, and I have to go there over here. But it won't ever go to that equilibrium. So I have regions of stable conditions. Another example, you could have let's say the old all-on curved surface. I could have a region of stable and a region out here unstable. Drops off. Right? I get it over here, falls off the cliff. And now I have a nonlinear system that has a certain region here. Only in this region is it stable. In fact, it might even be some region of velocities that make it unstable. So I could have a region around the origin that's stable. Outside that, it's unstable. Right? That is typical of a nonlinear system. Right? And the whole thing you do with these Luther functions is finding these regions stable. Make sense? Okay.
Got some notes on everything.
Let me show you a classic problem. I think I can reproduce it. There's a somewhat rabbits and foxes problem. Where you have rabbits and foxes. Okay? And if you look at the state equations thing, is a look at the time derivative of rabbits and foxes. The rate of rabbits is a function of what? Well, negative the number of foxes. Negative E. Right? But positive the number of rabbits. So you tend to read like rabbits. Right? But foxes. They're going to increase the number of rabbits. Decrease the number of foxes because they should get competition. And it might be according to some, let's say, A and B here. Some ratio, some constant there of how fast they reproduce or how many foxes they have sitting in there. Okay? So that's the state. Question is this? These rabbits and foxes off on an isolated island, is it a stable population or unstable population? And remember, this is kind of a classic, this is a made-up mathematical thing, but in ecological studies, you do have closed systems. Classic one's been studied for decades is up in the Lake Superior, Isle Royale. Have you heard of that? It's an island, it's a national park actually, up near Canada, it's actually U.S., where there are wolves and moose on this island. And got there about last turn of the century or something. They've been studying this thing for years of the relative populations of it. And it's this kind of problem. Now, a lot of wolves eat the moose, right? Not so many wolves. Moose breed, but they got problems, they overeat and things, so it's a fluctuating thing. The way to find out the lipid function to determine this. What's the first choice made to start? It's a function of states of time, states of R and F. Okay, so I'll start this one. R squared plus F squared, if that works. R is positive, F is positive. R is 0, F 0 is 0. Satisfies that condition. Any number of R's and F's, or it can have negative roundeds and negative boxes, but mathematically you can. It's always positive. The derivative of this is what? R dot, F dot. Put in our state equations. I have 2R. This is minus F plus 8 times R plus 2F R minus BF. All right. Work out everything here. So I have 2R minus 2RF plus 2AR squared plus 2FR minus 2BF squared. That's against that. And I have 2AR squared minus 2BF squared. That's just what? Stable or unstable? The choice of that lipid function is unstable. Because satisfies the condition as being greater than 0, b of 0, anytime is 0, but my derivative is non-negative for all states. Therefore, we conclude this population is unstable. Okay. Questions on that? Yeah.
What if B is much bigger than A? Negative.
Well, is there any value of R's? Assuming A's must be what? If A is negative, would that matter? Would that make it stable? Yeah. Well, what does that mean? It means we're apt to have the slower growth. Which you know, if you've been around rabbits, it's not the case. So this is saying that A better be positive, B better be positive. Therefore, this is an unstable population. Unless somehow you can make those coefficients zero, which is not going to be the case. Okay. All right. Questions on this stuff? We've done functions. I'm going to give you a nice little homework problem on these. Pretty easy, not too bad if I have second order type systems. Getting into third, fourth, gets a bit hairier. And if you take, say, nonlinear controls, you'll find all kinds of theorems and corollaries and whatnot, and determinants. How I can find reasonable stability.
try different, depends.
Certainly, you might try it. Is there one that we could try that maybe might work to show this thing somehow?
We could integrate,
Integrate what?
if we make it a -2 squared and integrate that.
Oh, you mean working backwards?
Yes.
Yeah, that's an approach that often you might try. So you can actually work this out. So since this is the case, going backwards on this, yeah, let's see if we can go backwards on this. That says, that could hurt if you do this way. N minus 2a y squared plus b f squared. Integrate this thing. We'll have a I'm going to put it into this sort of form, the R. Dawson, A dots, F dots. So, it's basic. Yeah, it's really tough because I really want it in terms of these derivatives of states, and it's not obvious how they come into this. Some problems you can do that kind of trick, but this one's not the easy one to do that. Pretty much in this problem, I have to go forward. There are some problems that actually done it backwards, but this one's not one that's a good one to do that. Yeah.
Sorry, I'm just thinking here, isn't it saying if there's a ton more wolves than rabbits, then it will be stable though? Am I thinking about this wrong? Like the.
Oh, being the original?
answer? Yeah,
No.
because it'll be negative if there's like, no, that's not what it means.
Means, well, you mean that this is somehow, or no, what it means is that
Positive.
for any values of R's and F's, is that going to be positive, negative, definite? I want it for any set. You could probably find a region, yeah, so if this would be less than 0, in fact, you can find the equilibrium says that this would be minus 2r squared equals minus f squared. That f squared over r squared. We're trying to do something like this. Is b over 1. If that were the case, then would it be stable somehow? Yeah, but not for all general cases. What it means is the population goes to 0. They all die off. But, yeah, okay, that's stable. That is the origin. Right? No rabbits, no foxes. Right, so if I have that many foxes, yes, it will go to an equilibrium, which is, the trivial answer.
Okay.
Yeah. Yeah.
So do we ever really care about like regional instability, or are we mostly just always?
Do we care about region? Yes, we do care about region stability for nonlinear systems. Because it means that, like, for instance, the annual problem or the ball on the rim of the crater means I better make sure my system never goes outside that region. If it does, I'm in trouble. Okay? And you might think about that of, almost any real physical system. Really all along linear. There's no such thing as a linear system. You think of airplanes, right? Yeah, it's stable in certain regions, perfectly fine. But there are certain regions, right, stalling, where it's unstable, right? Or flat spins, or whatever the other nasty things that can happen in an airplane. So as long as I'm within this region of speed, angle of attack, whatever, I'm okay. I go outside that region, I'm in trouble. Right? The airplane's a great example of that. I got to fly my airplanes, and if I get a half a minute in, I feel successful. And I don't have to tape them back together too bad. It'll I mean, think about, canoe or kayak, right? Yeah, okay, stable, certain region or something, right, lean over too far, get to the realm of I'm well wet. All boats and ships have that kind of problem. They're stable within certain regions, get so far, they're going to capsize. So again, there's regions that you want to make sure your system stays in. Even though within that realm, I might consider it to be a linear system, equations work well. But what realm does that assumption no longer hold? And that's a lot what we do in nonlinear controls. Because linear systems are great. Solve the equations, everything, solve this different, solve different equations. But what real systems are linear? Zero. There is no such thing. Right? It's a mathematical convenience that works well, hopefully most of the time, but not all the time. Okay? All right. We're about out of time. I almost forgot when this class gets out.
10:30.
10:30? All right, well, we have 5 minutes here. Any questions on this? I'll post a nice little homework problem.
So I'm kind of having a little bit of a hard time understanding a little bit of this concept. So we essentially just sort of guess at an equation, like for example.
Guess a Lyapunov function.
Yeah, a what?
You're guessing, or you're creating that Lyapunov function. You're guessing it satisfies the, and then you're checking, does that derivative, what's the derivative tell you?
Right. So we guess that Lyapunov function. We take the derivative, we check it, and so like from this. I guess kind of what I'm having a hard time understanding is like we've just taken these equations that we have just kind of guessed at, taken the derivative, and from that we've determined that the system is unstable. Would we then like, what, I guess it just feels arbitrary.
Region of stability. For instance, there's one problem we did. This one. This is done by energy. Just want to have the, oops. This is actually a Lyapunov problem.
So is this unstable or stable?